Thanks. So I'm going to talk about heavy hitters and clusterings, um, possibly with connections to coding theory as well. So this is joint work with Casper Green Larsen, Mika Thorup, and Jelani Nelson. All right, so let me start. We operate in the streaming models. In this setting, we start at the beginning of the stream with a vector initialized to 0. And then you receive a stream of updates in the form, I want to change the ith coordinate by the amount of v. So you keep receiving these updates that change the coordinate of the vectors. And you can think of the vectors to represent, say, all the computers in the network, where n, let's say, is 2 to the 32 if you operate on IPv4. And xi is just the number of packets sent by the ith machines. And you're operating the monitoring system of these communications among computers. And at some point in the stream of updates, the operator wants to query some estimate of some functions on the communication patterns of these machines. And the whole point is we want to be able to make these queries without storing the entire vector x. That is, you want the memory of the algorithm to be sublinear in the number of machines, to be little o of n. So this is a basic setup of streaming algorithm in general. And you could have many questions, different functions you want to query. For example, you want to count how many machines are communicating. That's the F0 problem. You want to look at the moments of the number of packets sent. That is the P frequency moments. You could have point query. That is, you want to know how many packets machine I is sending, and so on. So there are a lot of these functions that you might want to keep track in the streaming setting. But it turns out that for a lot of these functions, even simple ones, like the one I just mentioned here, you cannot get any bounds in sublinear space unless you are fine with both approximation and randomized algorithms. So that is the setting that we will most likely have to operate in sublinear space for most of these problems, including the very simple function like these. So this talk will look at one particular functions. Okay, so there are many streaming models out there as well, depending on how you want to restrict the different form of updates that could happen. So one is insertion only, when basically the x just keep increasing over time. You just keep adding 1 to the coordinates. The second more general model is a strict turnstile, where you allow to increase and decrease the coordinates. But it has to be the case that at all point in time, the value xi have to be non-negative. For example, the first one, you could think of the example where you count the number of packets sent by the machines. And the second one, let's say you want to count the number of connections by the machines. So the number of connections could increase when you open new connection. It could decrease when you close old connections. But the number of connections is always non-negative. And in the most general setting, which is the general turnstile, there's no restriction. You could have xi being positive or negative or mixed at any point in time. These three different models in increasing generality. And in today's focus, we'll look at one particular function, which is the heavy hitters. The L1 heavy hitter, to be precise, though similar results also hold for all the LP with P between 0 and 2. Okay, so what are the heavy hitters? So an index is a heavy hitter, an epsilon heavy hitter. It basically accounts for at least epsilon fraction of the total traffic on the network. That is the coordinate xi, that is at least epsilon times the L1 norm, the entire frequency vector. Right? And the query operation is we want to report the list of all the heavy hitters. So I said before, we have the set of approximations. So what that means is we're allowed to output a list where everything on the list have to be epsilon over 2 heavy, so that you can think of like a soundness condition. And 2, the list have to contain all the epsilon heavy items. So that is like a completeness condition. So the list you output have to be both sound and complete. So previous work on this problem. This problem has been studied for a long time with a lot of great ideas in the past. So I will not be able to go through all them all. So there are a lot of works in this area. So just highlight a few of the previous results. So one result is due to Kormod and Muthukrishnan on the very influential Kalman sketch, where they get excellent space of 1 over epsilon times log n. This is optimal. Very fast update time of log n operates in the most general model. The only downside, the query time of n log n. So it's pretty slow because you have to check every coordinate to find the heavy elements, even though we know there are only at most 1 over epsilon heavy coordinates, right? Because each of them account for at least epsilon fraction of the sum. So there can be only 1 over epsilon of them. But this query time is very slow. So to fix this problem, they also have a second solution based on combination of dyadic tree on top of the Kalman sketch, where you lose a little bit in the memory. So the space will be log square instead of log. But now you get a much better query time. And you also suffer a little bit in the update time. But the really great improvement here is the query time is so much faster. It's log square of n instead of n log n. And then later on, there's another result that changes dyadic tree. So this is a binary tree to a B tree, where it gives you a trade-off between the space and time in between these two results. So the B tree, for example, one particular choice of parameter you can pick is you could get the space to be optimal, 1 over epsilon times log n, just like the Kalman. But the query time have to be still some polynomial in n instead of the log square n here. This operates somewhere in between these two results from the Kalman paper. So all these results that I mentioned, they all succeed with high probability. That is, when you query it to output a list, the list will satisfy both the completeness and the soundness with probability 1 minus 1 over n. It's very high accuracy. So there seems to be some kind of trade-off here, as you can see, between the space and the query time in these results. And in this work, what we show is that you don't actually need this trade-off. You can almost get the best of all these in all these measures. That is, we can get the space to be the optimal 1 over epsilon times log n, get the optimal update time. I guess we don't know if it's optimal. So this is a big open question. How do you show lower bounds for update times? But it is as fast as all the previous results, which is log n update time. And the query time is polylog now. It's not polynomial in n like these results. And it operates in the general model, the general turnstile. And so here is the situation in the L1 heavy hitters. We also have results for all the other LP for p between 0 and 2. It's have similar bounds. You can check in the papers. You can also find a slightly stronger notion of heavy hitter called the tail heavy hitter. This is a bit technical, so I'll not talk about it. So the main idea in this work that we use is that you can see that the previous results are pretty good. You already get a very nice bound. It's just the only thing that seems to go wrong is in the query time. That is, the query time was polynomial. So it actually is a polynomial in the failure probability. That is the polynomial factor in the previous query time. So the main idea in this work is we try to reduce from the case we want, which is a high probability success, to the case where the failure probability can be reasonably large, 1 over polylog. So that is the main part that is missing from the previous results. And for this task, generally you could have the following idea that, okay, so I have a solution that succeeds with reasonable probability. Let's just repeat it a few times and then pick the majority answer. Unfortunately, if you perform this usual reduction, you blow up the memory, because if you repeat it log n times to get the high probability results, then you also use log n times more memory. And this is not desirable. So the entire goal here is how do you compose together many of these basic blocks that succeed with reasonable probability into one big new structure that succeeds with high probability. Right. So that is what we do. It's reduction from the reasonable success probability to high probability of success. Okay. So our algorithms have two steps. One is that we reduce from the case when epsilon is very small to the case when epsilon is reasonably big, about 1 over log n. So recall that epsilon is the threshold for the heavy hitters. That is, the heavy hitter have to account for at least epsilon fraction of the total mass. So we reduce from the general epsilon that could be tiny to the case when epsilon have to be at least 1 over log n. In other words, there are at most log n heavy hitters in this case. And then finally, we solve the case when epsilon is bigger than 1 over log n. The first step is just an exercise in concentration bound, so I'll not focus on that. It turns out that the main work is in the case when epsilon is reasonably big, 1 over log n. So we'll focus on this case. Okay, so the question I mentioned before was how do we stitch together multiple basic blocks from previous work to get a high probability bound. The idea we use is, so let's say 29 is a heavy hitter that we want to be able to identify. What we do is we encode it. Let's say I just write 29 in binary form. Because you could use it, you could use error correcting code, but here just for demonstration, I'll just write in binary purely and not put any code on top of it. So what I do is I'll break up this index 29, write in binary, break up the binary encoding into chunks, right? And then feed each of these chunks to one of the basic blocks, the B tree that I mentioned before. So the idea is the B tree is really good if I work with probability 1 over log n. So it will work very well if the indexes are small. So each of these blocks are only log n bits. So that's the ideal size for the B tree. And the idea is that if each of these basic blocks from previous work, the B tree, can deal with these chunks and find me the heavy chunks, then I can stitch together all these results from the different B trees together to solve my problem with the log n bits index. And the point is, each of these blocks can fail with probability 1 over log n, but I have log n over log n such blocks to deal with. And I can tolerate a constant number of them failing, a constant fraction of them failing. So you can multiply together all the failure probability to get the 1 over n failure probability. So that's the basic idea. That we just have these basic blocks from the previous work, and then you stitch them together to get to drive down the failure probability to 1 over n. So that's the basic idea. So the main questions is how do we stitch together these blocks? So it's very simple in the case when you just have one heavy hitter, because each of these structure would just return, I tell you the first guy, P1, the first B tree will tell me that 1 is heavy. This guy just tell me 3 is heavy. This guy tell me 1 is heavy. I just stitch together all these strings. I get the index 29 back. The problem is if I have 2 heavy hitters, each of these basic structure will tell me that there are 2 heavy hitters, and their chunks would have these 2 values. And then the next guy will say there are 2 chunks that are heavy, and so on. But now, how do I know which one to stitch together? So that's a problem. I don't know which chunk comes from the first heavy hitter. I don't know which chunk comes from the second heavy hitter to stitch together. So the remedy is we'll include in each of the chunk not just the essential information, but also some hash values so that I know which chunks come from the same heavy hitters so that I can stitch them together without stitching chunks from different heavy hitters together to create spurious wrong answer. That's the basic ideas. So here's a demonstration. So the first data structure will tell me, okay, say I have 3 heavy guys, and I give them their hash value to be black, yellow, and blue. And the second data structure will also have identified 3 heavy hitters, and the information and the hash value also black, yellow, and blue. So the nice thing is now I know to stitch these 2 guys together because the hash value are both black, so I know to match the black guy and the black guy. In general, what I include with each of the chunks is not just the index of the heavy hitter, but also the hash values of the chunk in the next data structure. So I can know these 2 chunks are of the same heavy hitter if the hash value was the same. So I draw this edge when they both store the same hash values. They're supposed to match if they're the same heavy hitters, and supposed not to match if they're different heavy hitters. So you can trace out a graph like this. If everything works perfectly, you can just you can build this graph based on the hash values, and then just compute the connected components to find the heavy hitters. And once you have all the chunks together, just decode the index of the heavy hitters. So now the problem is this line graph is not very robust. That is, if I just have one level that fails, then this situation could happen. Let's say I have just this one layer that failed, and I have a wrong connection here. Then the connected component algorithm failed. Right? I just go down this path, and here I go to the wrong side. So I make this big mistake, even though I just have one of these levels that fails out of all these many different levels. So you want a graph that is more robust to a small number of changes than the line graph. And the idea is instead we use expander instead of the line graph. So the idea is now for every chunk, you store the hash values for all the neighbors in the expander, so that if 2 guys are supposed to be connected on the expander, you just check if the hash value agree. And the key point is on the expander, you only have constant number of neighbors, so you don't store a lot more than on the line graph. So everything still works. So the whole point is now I have the following graph problems. You can just forget about heavy hitters and purely work in a graph setting. So this is also a really cool graph problem that somehow have not been dealt with before, which seems very natural problem. So I have a big graph, and on this graph, I could have multiple clusters. Each of these, we call it an epsilon spectral clusters, is an induced subgraph in this big graph, where the number of edges going outside the clusters is no more than epsilon times the volume of the cluster. That is, an epsilon fraction of the edges go out. Most of the edges stay inside. And secondly, internally, inside the cluster is very well connected. That is, if you split it into 2 halves inside the clusters, the number of edges going across the cut is almost as many as in the random graph. And the point is I want to give a partition of the original big graph so that I can identify all these spectral clusters. So the difference from a lot of work that so there are a lot of work in graph partitioning, but one of the features that are very different is here we want to find all the clusters. And secondly, the size of the cluster could be much smaller than the size of the entire graph, but we still want to find these clusters. This seems to be a very natural problem, but has not been dealt with before. So what we do is we recursively use Cheeger cut and crucially some local improvement steps to be able to find these clusters. The problem with things like recursive Cheeger cuts alone is that we could have very good cut on the average sense, but it totally could mess up one of these clusters. So if I have 4 clusters, it could get perfect cut on 3 of them, and let's say totally mess up the 4th one. That we don't want because we want to identify all the clusters. So So that is a problem. So the fix is we identify a closure property so that if we apply local improvement to ensure this closure property, then we ensure that the Cheeger cut can never, after improvement, will not mess up any of the cluster at all. So that's exactly what we do. That is, we start out with the Cheeger cut. We apply the local improvement to ensure that the closure property works. That is, if the original cut already find at least 2/3 of the cluster on one side, then after the local improvement, all of that cluster will go to one side. So that is a good case. The only case that is bad is at the beginning, the split could be even. Then you don't know what is the local improvement to improve because half of it is on the left side, half of it is on the right side. It's, you have to break tie somehow. So that's why we introduce this new step, that is to break tie. So we favor one side, move all the vertex with a lot of neighbors on the other side to that side to really tip the balance to one side. And then we apply the local improvement again, which will completely move that cluster to that side. So that will be done. This is on top of Cheeger cut, we apply several local improvement steps so that it will not mess up any of the small clusters. This seems to be a very cool algorithm that possibly have more applications beyond heavy hitters. So in conclusion, we show you can get essentially the best possible you can hope for heavy hitters, that you can get fast update time, fast query time, you get optimal space, and with high probability of success. And it works for all the LP heavy hitters for p less than or equal to 2. And as I mentioned, this graph partitioning problem seems like a very natural task. So it may be possible that our algorithms can be more widely applicable for other clustering or graph partitioning tasks. So that is a very interesting question to look at. And another question is, can you improve the query time to be just log n instead of polylog, perhaps by using better graph partitioning algorithms. So with that, I conclude.
Perhaps it's a very quick question, please, while the next speaker is setting up. Do you think it's possible to use local partitioning graph algorithms?
It seems tricky because local partitioning lose a lot of the relative size of the cluster compared with the whole graph. So that's usually true even in the other setting tools. But that would be interesting if it actually works. I'm not sure.